Right now, a spacecraft about the size of a small car is flying through the atmosphere of a star. It is closer to the sun than anything humans have ever built, moving fast enough to cross America in 20 seconds. And it is still alive. On one of its earliest dives, an instrument on board measured the sun's magnetic field and reported something impossible. The field was pointing backwards, away from the sun, then toward it, then away again, flipping like a switch. Nobody predicted it, and explaining it may solve a mystery older than the space age itself. To understand why a backwards reading from a magnetometer made solar physicists drop everything, you have to understand the problem that has haunted them for more than 80 years. The surface of the sun burns at roughly 10,000 degrees Fahrenheit. That is hot enough to vaporize any material we know of, but by the standards of stars, it is almost mild. The strange part sits above the surface. The sun's outer atmosphere, a vast halo of thin, glowing plasma called the corona, is hundreds of times hotter than the surface below it. In places, the corona reaches temperatures of more than 1 million degrees, and during violent events it can climb to several million. Think about how backwards that is. If you walk away from a campfire, the air gets cooler. The sun works the other way around. Move away from the burning surface out into the corona, and instead of falling, the temperature explodes upward. It is as if you stepped back from that campfire and the air around you suddenly became hotter than the flames. Physicists call it the coronal heating problem, and it was first noticed in the 1940s when scientists studying light from the corona realized the atoms there had been stripped of electrons in ways that only extreme temperatures could explain. For decades, every proposed answer stayed a guess because there was no way to check. The corona was 93 million miles away, wrapped around the most hostile object in the solar system. You could stare at it through telescopes, and during total eclipses you could watch it flare into view as a ghostly white crown around the blocked disk of the sun, which is where it got its name, since corona means crown. You could measure its light, model its behavior, and argue about it at conferences for an entire career. What you could not do was touch it, and in physics, a theory you can never test directly has a way of sitting unresolved for generations. Then, in 1958, a young physicist at the University of Chicago made the problem worse. His name was Eugene Parker, and he did the math on what a 1 million-degree atmosphere would actually do. His calculations said the corona could not just sit there. Plasma that hot would overwhelm the sun's gravity and escape, streaming outward in every direction past the planets, filling the entire solar system with a constant supersonic wind of charged particles. He called it the solar wind, and it carried a startling implication. Our planet, along with every other world in the solar system, is submerged inside the outer atmosphere of a star. The reaction from the scientific community was brutal. Reviewers rejected his paper and suggested he go back and study the subject properly before writing about it again. The idea of a supersonic wind blowing off the sun sounded absurd. The paper only survived because the journal's editor, the famous astrophysicist Subramanian Chandrasekhar, could not find an actual error in the math and published it over the reviewers' objections. 4 years later, the Mariner 2 spacecraft flew toward Venus and measured a constant stream of charged particles rushing past it, exactly as predicted. The solar wind was real. Eugene Parker went from ridiculed to vindicated, and solar physics gained 2 enormous questions in place of 1. What heats the corona to millions of degrees, and what accelerates the solar wind to more than 1 million miles per hour? Those questions were not just academic. The solar wind slams into Earth's magnetic field every second of every day. When the sun erupts, that wind turns into a storm that can fry satellites, scramble navigation systems, expose astronauts to dangerous radiation, and in extreme cases, shut down power grids on the ground. We live inside this star's atmosphere. Our entire technological civilization is exposed to its moods, and for 60 years, we could not explain how its 2 most basic engines worked. Scientists knew what they needed. They needed to send something into the corona itself, to sample the fire directly. As early as 1958, the same year as Parker's paper, a national committee listed a solar probe as a priority mission. Then the idea sat on the shelf for almost 60 years because nobody could figure out how to build a machine that flies into a star and survives. Heat is only half the problem. The other half is getting there at all because reaching the sun is, strangely, one of the hardest journeys in spaceflight. Earth is moving sideways around the sun at about 67,000 miles per hour, and anything we launch inherits that sideways speed. To fall inward toward the sun, a spacecraft has to cancel most of that motion, which takes far more energy than leaving the solar system entirely. It is easier to reach Pluto than to reach the star sitting in plain sight. By the 2010s, engineers at the Johns Hopkins Applied Physics Laboratory in Maryland believed they could finally solve both problems, and NASA gave them the chance. The mission was named Parker Solar Probe, after Eugene Parker himself. It was the first time NASA had ever named a spacecraft for a living person. Parker was 91 years old when he stood in Florida in August of 2018. and watched a Delta IV heavy rocket, one of the most powerful launch vehicles on Earth, carry his namesake into the sky on a pillar of flame. The spacecraft it carried is a masterpiece of controlled paranoia. Its most important component is a heat shield, a disk of carbon composite about 8 feet across and only 4.5 inches thick, with a core of carbon foam that is mostly empty air. During the closest passes, the sunward face of that shield heats to around 2,500 degrees Fahrenheit, hot enough to glow. Just a few feet behind it, in the shadow where the instruments ride, the temperature stays near 85 degrees. The shield holds a blazing furnace on one side and a warm spring afternoon on the other, separated by a few inches of carbon. The trick works because the space near the sun, for all its ferocious energy, is nearly empty. Heat needs matter to carry it, and the corona is millions of times thinner than the air you're breathing. The shield takes the full blast of the sun's light, but the thin plasma around the spacecraft, despite its million-degree temperature, barely touches it. The same way you can wave your hand through the air of a hot oven without burning, as long as you never touch the metal. Everything depends on keeping that shield pointed at the sun. Near closest approach, the spacecraft is so deep in the sun's gravity well and moving so fast that radio commands from Earth are useless. Light itself takes about 8 minutes to cross the distance. By the time controllers saw a problem, the probe would already be dead. So the engineers gave it reflexes. Sensors along the edges of the shadow detect the first touch of direct sunlight on the spacecraft's body, and the probe corrects its own orientation within seconds, on its own, with nobody watching. It even cools its solar panels with circulating water, pulling them back into the shadow as it dives, leaving only the tips exposed to drink in the light of a star from point-blank range. The plan was patient. The probe could not simply dive into the sun. Instead, it would use Venus as a brake, flying past the planet again and again, 7 times in total, each flyby bending its orbit and dropping it closer to the solar surface. The trajectory called for 24 orbits, spiraling inward over 7 years, with each dive plunging deeper than the last. In November of 2018, on the very first close pass, Parker Solar Probe skimmed about 15 million miles above the solar surface and instantly became the closest human-made object to the sun in history. Then, the data started coming home and the story changed. Among the instruments riding behind the heat shield is a suite of antennas and magnetometers built to measure electric and magnetic fields directly. Essentially, a compass and a voltmeter dipped into the atmosphere of a star. Scientists expected the magnetic field to behave, on average, in a simple way. Near the sun, the field lines should point outward or inward along a smooth direction, like the spokes of a wheel, with turbulence layered gently on top. That is what made the first readings so disturbing. Again and again, for stretches of seconds to minutes, the magnetic field flipped. A field line pointing away from the sun would suddenly reverse and point backwards, toward the sun, as if the compass needle had spun around. Then, just as suddenly, it would snap back to normal. Meanwhile, the solar wind flowing past the spacecraft briefly accelerated during each reversal, jumping in speed like water surging through a kink in a hose. The team called them switchbacks, after mountain roads that fold back on themselves. What the spacecraft was flying through, physically, were enormous S-shaped kinks in the sun's magnetic field, magnetic hairpins, hundreds of thousands of miles long, whipping past the probe like a cracked rope. Down at its source, the field still pointed the right way. The lines were simply bent so violently that where the spacecraft flew, they aimed backwards. A few backwards readings could have been dismissed as instrument noise. This was the opposite of rare. During the early encounters, the spacecraft counted switchbacks by the 1,000. Close to the sun, the supposedly smooth solar wind revealed itself as a torrent of magnetic kinks, one after another, and nothing in the standard picture of the corona had predicted them. Here is where the discovery gets interesting, because a bent magnetic field line is not just a curiosity, it is a battery. Plasma physics is unforgiving about geometry. A kinked field line stores energy the way a bent bow stores energy, and when it straightens out, that energy has to go somewhere. It goes into the surrounding plasma as heat and as motion. Suddenly, the 2 ancient questions, what heats the corona and what accelerates the wind, had a new suspect. If the region around the sun is saturated with these magnetic hairpins, and each one releases energy as it relaxes, then the switchbacks could be delivering exactly the kind of distributed, relentless heating that the corona demands. Not one giant explanation, but trillions of small ones, a star heating its own atmosphere by constantly cracking magnetic whips through it. Then the next round of data made the story stranger. As the orbit tightened and the probe dove deeper, the switchbacks did not fade. They grew more common, and they started showing structure. They arrived in patches, and the patches matched a pattern on the sun below. The sun's surface is tiled with convection cells called supergranules, rising and sinking currents of plasma, each one roughly the size of Texas, stacked many times over, and the funnels of magnetic field that emerge between those cells lined up with where the switchbacks were flowing from. The kinks were not forming randomly in space. They appeared to be born low, near the solar surface, in the same magnetic funnels suspected of launching the fast solar wind itself. That points at the origin story. Where the funnels emerge, magnetic field lines pointing in opposite directions get shoved against each other by the churning surface, and they do something plasma physicists call reconnection. The field lines snap, break, and splice themselves together in new configurations, releasing bursts of energy and launching fresh kinks outward like sparks off a grinding wheel. If that picture is right, the backwards readings Parker recorded are the fingerprints of the exact process that turns a star's trapped magnetic energy into wind. 60 years of theory, the answer may have been written in a compass needle flipping the wrong way. The debate over the details is still alive, which is exactly how science at a frontier is supposed to look. Some researchers argue the kinks are born in those reconnection events near the surface and survive the long climb outward. Others argue the wind itself manufactures them higher up, as faster streams plow into slower ones and shear the field into folds. The two ideas point to different engines for the solar wind, and the only referee that matters is a spacecraft that keeps flying deeper and measuring which prediction holds. Every dive since has been another round of that argument, settled one magnetic reading at a time. Before we go deeper, this channel exists to follow stories exactly like this one. Spacecraft still out there right now, sending home discoveries that rewrite the textbooks. New missions cross new thresholds every few months, and the sun is heading through the most active stretch of its cycle. If you want to be here when the next set of impossible readings comes home, subscribe, and let's get back to the part where this spacecraft actually enters the sun. Because everything you have heard so far happened in the solar wind, close to the star, but still technically outside it. The sun does not have a solid surface where the star ends and space begins, but it does have a real boundary. Physicists call it the Alphen surface. Inside that boundary, the sun's magnetic field is strong enough to hold onto its plasma, and waves in the field can still travel back down toward the surface. The material there is bound to the star. It belongs to the sun. Outside the boundary, the wind has won. The plasma is moving too fast to ever turn back, and it is lost to space forever. Crossing that line, in the physical sense that matters, means leaving the solar wind and entering the sun itself. For decades, nobody knew exactly where that boundary sat. Estimates put it somewhere between 4 and 9 million miles above the surface, but it had never been measured because nothing had ever been there. On the 28th of April, 2021, during its 8th dive, Parker Solar Probe was descending through the corona when its instruments registered the change. The magnetic field strengthened and took command of the plasma around it. The wind conditions inverted. The spacecraft had crossed the Alphen surface about 8 million miles from the sun, and for the first time in history, a machine built by human hands was flying inside a star's atmosphere in the fullest sense, surrounded by material that still belonged to the sun. For roughly 5 hours, humanity was inside its own star. Think about what that means. Every previous milestone in exploration involved reaching a place, a shoreline, a summit, a lunar plane, somewhere a flag could stand. This one involved entering an environment that would erase a flag, a human, and most machines in seconds, and lingering there long enough to take careful measurements. The samples it gathered in those hours came from plasma that was still gravitationally and magnetically bound to the sun, material that had never left home. When NASA announced the crossing that December, they put it simply: a spacecraft had touched the sun. It remains one of the shortest sentences ever to summarize 60 years of ambition. And the boundary itself turned out to be alive. Instead of crossing one smooth line, the probe punched in and out of the sun repeatedly on later orbits, because the Alphen surface turned out to be wrinkled rather than round, with towering spikes and deep valleys that rise and fall as the sun churns. So the spacecraft threads through a boundary that is constantly reshaping itself around it. Inside those crossings, the plasma was calmer than the wind outside, and switchbacks grew scarce. One more clue that the kinks are born in specific magnetic funnels rather than everywhere at once. Every discovery so far had been achieved at a relatively cautious distance. The true target still lay ahead, and reaching it meant surviving the most dangerous maneuver of the mission. On the 6th of November, 2024, the probe swung past Venus for the 7th and final time. That flyby set the endgame. The orbit it created would carry the spacecraft to within 3.8 million miles of the solar surface, the closest that any human-made object has ever come to a star. To picture that distance, imagine the space between the sun and Earth shrunk down to the length of a football field. Earth sits in one end zone. The sun fills the other. Parker Solar Probe crosses the 4-yard line. The dive was scheduled for the 24th of December, 2024. which meant the most dangerous moment of the mission would arrive on Christmas Eve. And the geometry of the encounter came with a cruel catch. During the days surrounding closest approach, the sun itself would sit between the spacecraft and Earth, severing communication almost completely. The probe would make the most dangerous passage in the history of spaceflight completely alone, running on its own reflexes, while its builders spent the holidays waiting in silence. Consider what the machine had to do by itself. At closest approach, it was moving at about 430,000 miles per hour, the fastest any human-made object has ever traveled, fast enough to fly from Washington to Tokyo in under a minute. Its shield was soaking up the light of a star from less than 4 million miles away, shedding heat at more than 2,000 degrees, while the instruments behind it sipped data at room temperature. A single uncorrected wobble lasting longer than a few seconds could have exposed the spacecraft's body to direct sunlight and ended the mission instantly. There was no ground control, no second chance, and no way to call for help. Picture the operations room at the Applied Physics Laboratory during those days. The mission's engineers had spent years building the probe's reflexes, precisely so that this moment could happen. And now the finished machine was beyond their reach, diving through the corona at record speed, while its telemetry screens on Earth sat quiet. Some of them had worked on this mission for over a decade. All they could do was calculate where the spacecraft should be, trust the systems they had built, and wait for a window when the geometry would allow a whisper of radio to slip past the sun. 2 days after Christmas, a signal reached a dish on Earth. It was only a beacon tone, the simplest message the probe can send, but it meant one thing. The spacecraft was alive and healthy. It had flown through the atmosphere of a star at record speed, on its own, and come out the other side still doing science. When the full data came home, it included something no one had ever seen. The probe's camera, a wide-field imager designed to photograph the solar wind, had been taking pictures from inside the corona. In 2025, NASA released those images, the closest views of the sun ever captured, showing streams of solar material and the aftermath of eruptions from the inside, including collisions between solar storms that forecasters on Earth could barely see at all. For scientists who study space weather, it was like moving from satellite photos of a hurricane to flying a plane through the eye. That brings the story back to the present, because everything you have just heard leads to a mission that is still unfolding right now above your head as you watch this. Parker Solar Probe has kept diving at that record distance ever since, pass after pass, matching its own records for distance and speed roughly every 3 months. On the 8th of June, 2026, it completed its 28th close approach to the sun, once again skimming 3.8 million miles above the surface, once again out of contact and flying on its own reflexes for 9 days around the encounter, and once again checking in afterward with a beacon tone that told its team the machine was healthy. The primary mission formally ended in the summer of 2025, with every original objective met, and the spacecraft simply kept going. It is out there at this moment, healthy, circling the star that has been trying to destroy it for 8 years. The timing could not be better. The sun runs on a cycle of roughly 11 years, swinging from quiet to violent and back, and it is currently near the active peak of that cycle. Sunspots multiply and eruptions grow more frequent, and this probe is measuring the storm from inside, while the rest of us watch from 93 million miles away. Every pass through the solar maximum captures conditions that no spacecraft has ever sampled up close, the raw source of the space weather that threatens satellites, astronauts, and power grids down here. The stakes of that forecasting problem keep growing. Tens of thousands of satellites now orbit Earth. Astronauts are preparing to travel back to the Moon and eventually onward to Mars. And a severe solar storm on the scale of the strongest events in recorded history could disrupt power and communications across entire continents. Predicting those storms means understanding the engine that fires them, and the engine is exactly what this spacecraft is parked inside of. And there is real suspense in what comes next. The spacecraft has outlived its primary mission, and NASA is now formally reviewing its future beyond 2026. The machine still works. The star is still erupting. Whether the dives continue for years to come or the program winds down while the probe is still healthy is a decision being weighed right now, which makes every one of these encounters feel a little more precious. Eugene Parker lived to see most of this. He watched the launch in 2018, the first person in NASA history to see a spacecraft carrying his name leave the Earth. He lived to see it confirm the solar wind's strange structure up close, and he lived to see it touch the sun. He died in March of 2022, at 94 years old, 64 years after reviewers told him his ideas were nonsense. His spacecraft is still flying. Somewhere over your head right now, on the far side of the daylight, a small car-sized machine is falling around a star. Shield glowing, instruments listening, catching magnetic field lines as they whip past, pointing the wrong way. The backwards readings that once looked like a malfunction are now the closest thing we have to an answer for why the sun's atmosphere burns hotter than the sun. The man who was told to go study the subject before writing about it again ended up with his name inside a star. The compass that pointed backwards ended up pointing at the truth. And the light touching your window today passed a tiny, stubborn spacecraft on its way here, still flying, still measuring, still listening to the sun.